Today we're going to be talking about biconditional statements and Venn diagrams. We will know when to use and be able to write a biconditional statement. We will be able to interpret Venn diagrams and use them to represent set relationships such as intersection and union. And we will recognize and use symbols of formal logic. So what is a biconditional statement? A biconditional statement is true both ways, meaning that the conditional and the converse, which if you remember from last class, which is the order of the hypothesis and conclusion, are both true. The format for a biconditional statement will have the hypothesis first, and then we say if and only if, and then we have the conclusion at the end. Now, instead of writing out if and only if, it is often abbreviated using the abbreviation IFF. Symbolically, it would be P, our hypothesis. If and only if is a double arrow because it points in both directions, like we said at the beginning, and then Q for our conclusion. So let's look at an example. Write the converse of each statement. If the conditional statement and the converse are true, construct the biconditional statement. Then translate each statement into symbolic form using your own letters. So our conditional says, if the sides of a triangle are congruent, so that'll be our hypothesis, then the triangle is equilateral. The triangle is equilateral will be our conclusion. So if you recall from last class, converse switches the order. So we would say if the, and a lot of times in geometry, instead of writing the word triangle, we just draw a triangle. So if the triangle is equilateral, then the sides of a triangle are congruent. So let's determine whether or not these are true. If the sides of a triangle are congruent, which means they're all the same size, then the triangle is equilateral. Well, equilateral means same sides, so this is true. If the triangle is equilateral, meaning all the sides are the same, then the sides are congruent, and congruent also means that they're the same. So they're both true. So to write this, we start with the hypothesis. We don't use the if. So we will start with the triangle, the sides of a triangle are congruent. Since it's a biconditional, in between we will have if and only if, which I'll abbreviate with IFF. The triangle is equilateral. How would we write this symbolically? I'm going to use P for my hypothesis and Q for my conclusion. So the conditional would be P, then Q. Converse switches the order, so it would be Q, then P. And the biconditional, we're going to write in alphabetical order, so P, if and only if with the double arrow, Q. So let's summarize some of the symbolic notation we've already talked about and some new ones. The first one is our arrow that just points to the right. That's our if-then statement. If we use a double arrow, then that's for if and only if. And we also have the squiggly for not. Some new symbols we're going to add to our list is, it looks almost like an upside down V. It also looks like how you would start to write a capital A, and it stands for and. So if it looks like a capital A, it means and. If we flip it over, that's or. It kind of looks like that little space in the R, or. And then finally, we have 3 dots and a triangle, which mean therefore. So let's write some statements into symbolic notation. They tell us here that P will represent a quadrilateral that has 4 sides. Q will represent a rhombus is a quadrilateral. R will represent a rhombus has 4 sides. And S will represent a rectangle is a quadrilateral. So, in example number 3, it says a rhombus has 4 sides. And a rhombus is a quadrilateral. So, a rhombus has 4 sides. We said it's going to be represented by the letter R. The and in the middle is going to be our and symbol that we just learned about. And a rhombus is a quadrilateral is represented by letter Q. A quadrilateral has 4 sides. And a rhombus has 4 sides. Therefore, a rhombus is a quadrilateral. Because of the therefore, we're going to do something special. So I'm going to leave some room below what I start to write. A quadrilateral has 4 sides is P. And is our symbol that looks like the beginning of a capital A. A rhombus has 4 sides is R. The therefore is a conclusion, so we're going to write it underneath our original statement. Therefore is our 3 dots and a triangle. And then finally, a rhombus is a quadrilateral is represented by letter Q. Our last example. If a rhombus is a quadrilateral, or a rectangle is a quadrilateral, then a quadrilateral has 4 sides. Since it's an if-then statement, we know we'll have our arrow. So let's look at the beginning. If a rhombus is a quadrilateral, Q, or our upside down or our V looking shape, a rectangle is a quadrilateral, S. Since both of these are part of the if statement, we're going to put them in parentheses to group them together. Then a quadrilateral has 4 sides is letter P. And that's the only thing that comes after the then, so it's the only thing after the arrow. So statements can also be represented using Venn diagrams. Venn diagrams show relationships among sets they are made of rectangles which represent universal or all-encompassing sets and circles which represent the smaller sets or subsets. So what is a set? A set is a collection of objects or numbers called elements. So we have the biggest set would be the universal set. Those are represented by rectangles. Within those rectangles, we'll have circles, which are smaller sets. And then inside those sets, we have elements, which are the objects or numbers that fit into those sets. So let's look and see how some things are represented using Venn diagrams. The first set notation is A union, which union is a U, B. These are the elements that are contained in A or B. Now, if you recall from earlier, when we were writing in symbolic notation, the or looked like a V. So or is pointed when it's in symbolic notation, but it's curved when we use set notation. In our picture, we want anything that's in A, so this whole circle, as well as anything that's in B, this whole circle. Next we have A intersect B, which looks like an upside down U. This means the elements contained in both A and B. In set notation, it looks like an upside down U. In symbolic notation, it looks like an upside down V. So they look similar, but they're just a little different for set notation than symbolic notation. Since we only want the ones that are in both, we would only be concerned about the stuff that overlaps from A and B. Not A, which the not symbol in set notation is the same as symbolic notation, means anything that's not in the A circle. So the B part that doesn't overlap, as well as outside the circles. That's the areas that would be not A. So we're going to use a Venn diagram to see if the following statements are true or false. So the first one is saying no trapezoids, which is this circle here, are parallelograms, which is this circle here. Since the trapezoid circle does not overlap with the parallelogram, this is true. There are no trapezoids inside the parallelogram circle. Next, all rectangles, so our whole rectangle circle, are parallelograms. If this is true, the entire rectangle circle will be inside the parallelogram circle, which it is. So this is also true. Some rectangles, so the rectangles, are trapezoids. If some rectangles are trapezoids, there would be overlap between rectangles and trapezoids. So this is false. We could either say no rectangles are trapezoids to make it true, or we could say some triangles, or let's look at the next one, sorry. Some triangles are rhombuses. Do our rectangles overlap with rhombuses? They do, right in here. So that is true. So if it says no, there's no overlap. If there's all, the smaller group will be inside the bigger group completely. And if it's some, you'll just have some overlap. Now let's put some numbers into our Venn diagram. So assume a game that included 200 quadrilateral pieces. So we know there are 200 quadrilaterals, had 100 parallelograms, 30 rectangles, 20 rhombuses, 8 that were both rectangles and rhombuses. Now, because of the 8 in this overlap, there's not actually 20 in this part of the circle. There's only 12 because 8 of them are accounted for in the overlap. Same with the rectangles. Because there's 30 here, but there's 8 in the overlap, there's really only 22. So now we have all the information we need to answer these questions. How many parallelograms, so of the 100, are neither rectangles or rhombuses? Well, we're starting with 100 parallelograms. We don't want the 22 rectangles, we don't want the 12 rhombuses, and we don't want the 8 in the overlap. So that means there are 58 parallelograms that are neither rectangles or rhombuses. How many rhombuses are not rectangles? So the ones that are rhombuses but not in the overlap would be the rhombuses that are not rectangles, so there are 12. If there are 25 trapezoid pieces, how many quadrilaterals are not parallelograms or trapezoids? Well, of the 200 quadrilaterals, we don't want parallelograms and we don't want trapezoids, so there are 75 pieces. How many rectangles are also trapezoids? These circles don't overlap, so there are 0. Finally, for your summary, draw a Venn diagram that represents what it would look like if it's an all statement. Draw a Venn diagram that would demonstrate a sum statement, and draw a Venn diagram that would represent a none statement.